Dr. Caleb Meyer is a software engineer at Parsons Government Services for the last 2 years. Since joining Parsons, he has investigated and implemented a number of features to improve the query performance of Apache RIA. There it is. Caleb earned his PhD in mathematics from UC San Diego and a BA in mathematics from Yale University. Welcome, Dr. Caleb Meyer.
Thank you. Hello, everyone. Thanks for coming. The title of our talk today will be RIA, Accumulo Indexing Strategies for Searching Semantic Networks. The work I'm going to be talking about today was funded by the Office of Naval Research and the National Geospatial Intelligence Agency. This presentation was funded by Parsons, and the work is a collective effort of the Parsons RIA team and the RIA founders. So today we're going to talk a little bit about RIA and a couple of indexing strategies that we've implemented for improving query performance with RIA, namely Materialized Views and our Entity-Centric Index. So let's start by talking a little bit about RIA. So RIA is an incubating Apache project. It's a RDF triple store that's built on, currently built on top of either Accumulo or MongoDB. And RDF is a W3C standard for representing linked graph data. Statements are serialized as triples, which consist of a subject, a predicate, and an object. So here at the bottom of the slide, we have a couple of statements. Caleb works at Parsons, Caleb lives in Virginia, and we have the corresponding RDF graph on the right. So you can see that nodes in the RDF graph correspond to subjects and objects, and predicates correspond to the edges between them, where the predicates are directed from subjects to objects. The language we use for querying RIA is Sparkle. It's a very expressive language that allows you to search your triple store for subgraphs. It has a SQL-like syntax in that you have a familiar select clause and a where clause. Variables appear in the select clause, and they're indicated by question marks. And within the where clause, you have statement patterns. So statement patterns are a lot like statements, except that you're allowed to have variables within statement patterns. So here we see in this Sparkle query, we were asking for all people who work at Parsons who live in Virginia, and we see the variable people appear in the subject position of both statement patterns. And something to note is that joins are performed somewhat implicitly within Sparkle, in that statement patterns with common variables have joins performed across them. So RIA is an implementation of an RDF4J interface. RDF4J is an open source Java framework for querying and storing RDF data. And it provides a couple of abstractions and interfaces for interacting with the underlying data store. The most important from a RIA perspective is the SAIL interface, which SAIL stands for the storage and interface layer. So here in our diagram, we can see that the Sparkle query comes in. It gets parsed by the SAIL layer. A query plan is generated, and then the implementation of the SAIL layer interacts with the underlying data store, which is Accumulo in this case. So at its core, RIA is a composite index which consists of 3 tables: the SPO, the POS, and the OSP table, where SPO stands for subject, predicate, object, POS, predicate, object, subject, etc. The reason the tables are named this way is because of how the triples are written within the row ID. So we write the actual triple within the row ID. So for example, in the SPO table, we write the triple as a subject, predicate, and object within the row ID. We can store the graph name or context, as it's sometimes referred to, within the column family. And the benefit of writing our keys in this way is that given any statement pattern with a constant, we can do a very efficient range scan for that statement in one of the corresponding index tables. And if you enable locality groups, you can do very efficient scans for subgraphs in your triple store. So this slide just provides an overview of how queries are evaluated within RIA out of the box. So this query is asking for all people who live in Virginia and who commute by bike and where they work at. So on the right, you can see how the query is parsed. So out of the box, the execution plan for the query the execution is such that the leftmost node is the topmost statement pattern that occurs within the where clause. And we see that we first evaluate the left most statement pattern. We pass those results into the next statement pattern, and then those results are passed up after that join is formed to the final statement pattern. So let's just walk through that evaluation process. So the first scan to evaluate x works at y, we would scan the POS table, because the only constant that appears in x works at y is works at, which is the predicate. And in scanning that table, we find that Bob works at Netflix, Greta works at Parsons, and John works at PlayStation are all triples in our data store. We then take the the values corresponding to the common variable between x works at y and x lives in Parsons, namely the x values, and use those to form ranges to evaluate the next statement pattern. So we take x equals Bob, x equals Greta, and x equals John, and use those to form ranges to evaluate x lives in Virginia. So in this case, we form ranges, Bob lives in Virginia, Greta lives in Virginia, and John lives in Virginia. We pass those in, and we find that only Greta and John live in Virginia. And finally, we take the values associated with the common variable, x lives in Virginia. We take the values associated with the common variable x lives in Virginia and x commutes method bike, and pass those into, use those to form ranges for the final scan. So again, it's just the x values, so Greta and John, and we form the ranges Greta commute method bike and John commute method bike, and we find that only Greta commutes by bike. And so the answer to this query would be x equals Greta and y equals Parsons. So out of the box, RIA evaluates all these joins on the client to a large extent. And these joins are sort of a combination of a nested loop and a hash join. And we can sort of use the batch scanner to kind of boost performance to a certain extent. So for example, in step 2, when we pass in the ranges, Bob lives in Virginia, Greta lives in Virginia, and John lives in Virginia, we could pass those all into a batch scanner and evaluate those in a distributed fashion. And we get some performance gains out of that. But in general, for anyone who's had to deal with client-side joins, they're a bottleneck. So the strategy is to come up with ways to push joins to the server as much as possible, right? Move the processing to the data. So the two approaches that we've come up with are Materialized Views and Entity-Centric Index. So for Materialized Views within RIA, the idea is we pre-compute queries of interest. We store those results in an Accumulo table, and then when a user issues a query, we match subqueries of that given query to representative queries of the results we've cached. And in that way, we're essentially reducing the number of joins that are required to evaluate that query. For our Entity-Centric Index, we essentially have designed it so that it's a distributed document partition index, and we can use intersecting iterators to perform merge joins of what we call entity-centric queries. So an entity-centric query, in this case, is queries where the statement patterns all share a common variable. So this query here in the upper left-hand corner would be an entity-centric query. So let's first talk a little bit about materialized views in RIA. So a little bit about terminology. So I'm going to use the term materialized view and precomputed join somewhat interchangeably. So materialized views is a sort of a relational database term that sort of refers to cache queries. And you can basically store your results in an actual table, which you explicitly refer to when you write your query. Whereas for precomputed joins, we don't explicitly refer to the cache results that we're interested in. We essentially have a collection of tables which store our cache results, and during query planning, we actually pull those in and we attempt to match those with subqueries of the user-issued query. So it's much more implicit in that way. So what I've just outlined here on this slide is a few things that maybe should be taken into account when you're thinking about queries that you want to cache. So I sort of think of, when I think of materialized views, I think of there being two key aspects to materialized views, namely figuring out which queries you want to cache and how to maintain those queries. So the majority of this talk, pretty much all of it, is going to be about how to maintain your results that you store, keeping that data fresh. But given that caching strategies is sort of an area of open research for us, I kind of just wanted to mention a few of the ideas that we have. So some things to take into account are obviously user preference. You want to be able to cache your own queries. Which queries have been used most recently. The query complexity, so the number of joins in the query. Maybe you have cardinality tables, selectivity tables, which give you a measurement of the number of intermediate results that a query is going to generate, and then relevance to your data and relevance to users. So maybe taking a frequent subgraph approach or looking at query logs to find common patterns in queries that are issued. So how do we actually use a precomputed join in RIA? Well, the idea, as I've mentioned, is we store our results in a precomputed join table. Here in the lower right-hand corner, we see such a table. And we have a query that's representative of that table. So select AB, where A lives in DC and A talks to B. And user issues the query there indicated in the middle of the slide. So we want to find all people who live in DC and the people that they talk to who live in Arlington and commute by bike. So what we do is we look at the user issue query and we look at the statement patterns in that query. And we say, okay, well, the top two statement patterns, up to maybe some variable relabeling where we send A to Y and B to X, are a match of the statement patterns in our representative query for our precomputed join. So we say that's a match. And then we package those nodes together into what we call a precomputed join node. And at query time, that precomputed join node effectively scans the precomputed join table. And we've essentially reduced our resulting query plan from one that has 3 client-side joins to now one that has 2 joins. So the rest of the talk here about as far as materialized views or precomputed joins is concerned is going to be about maintenance. So how do we keep data in our cached queries fresh? So there's 2 general strategies that we considered. So batch updates, so map reduce jobs where we recompute the queries periodically. The benefit of that is we're not adding much complexity to the system, and we're minimizing our data plume in that we're not having to keep a lot of intermediate results around. The drawback of that is that you're redoing a lot of work, and your data gets stale, right? Between your batch jobs, right? If data is ingested into the core tables, then your data is not your data is not reflective of your core RIA table. The other approach is incrementally updating your data, your cache query results. And so you use some sort of observer framework so that as triples are ingested in the system, they get joined with intermediate results that have been stored. And the benefit of this is our data is a lot fresher, right? We don't suffer from the data staleness problem. And the drawback, of course, is the data plume, where we're storing intermediate results and added complexity, right? We have to have an observer framework in place to kind of oversee all this. So we decided that fresh data was sort of much more important than having the increased data plume. And we decided to use Fluo to incrementally update our cache query results. So for those of you who aren't familiar with Fluo, there's going to be a talk right after mine about Fluo. It's an incubating Apache project. I hope I'm not stealing Keith Turner's thunder too much by talking a little bit about it now. Hopefully it serves as a nice introduction for what he's going to talk about. But Fluo is a Accumulo implementation of Percolator, which was described in a Google paper. And it provides multi-row transactions and the observer framework that we're interested in. And its use cases align very nicely with ours. Namely, we would have a large cache of data that we want to join with new data as it enters the system. So observers work in Fluo in the following way. Essentially, you have an observer monitor a given column in the Fluo table. And when new data is inserted into the column that the observer is watching, a notification is generated, and the observer processes that notification. What the observer does when it processes that notification depends on how its process method is implemented. And essentially, that process method takes in the row and column of the cell that's been changed, and it usually performs some sort of transformation on that data and writes it to some other column in Fluo. So in this way, you can chain these observers together. So you can take simple incremental updates, chain them together to perform much more complex incremental updates. So data comes in, it gets inserted in a column. The observer watching that column processes that data, writes to some other column, and the corresponding observer to that column then does something. And in this way, you can chain things together and perform complex incremental updates. So this diagram here just kind of indicates how we've formulated the process of updating a RIA query in this observer framework. So essentially, we have an observer that directly corresponds to each component of our parse query. And when a user registers a query with Fluo, there's metadata that's entered into the Fluo table that essentially tells Fluo what the content of the query is and essentially how it's pieced together, right? What the query tree looks like. And so let's just walk through how the results percolate up as they stream in. So here we have 3 triples stream in. Alice talks to Bob, Charlie talks to David, Bob works at coffee shop, and Eve works at pizza place. So we see that on the left, Alice talks to Bob and Charlie talks to David, match the statement pattern on the left. And Bob works at coffee shop and Eve works at coffee shop, matches the statement pattern on the right. Then we essentially, the statement pattern observer will get the parent of the given statement pattern node and say, what's my sibling? And then scan the intermediate results for that sibling to perform the join. So in this case, we take the common variable of the 2 statement patterns employee and look for values that match. So we have employee equals Bob, matches on both sides. So that result then gets written to the join column, which gets, since it's the top of the query, gets pushed out to a result observer, which then pushes that result out to an external table. So I'll go through the overall view of the app here in a second. So just to provide another example, we get another triple which gets inserted in the system. David works at coffee shop and matches the statement pattern on the right. We then look for values on the left that match the join variable employee. We see that there's an instance of David on the left. We perform that join and then we push it out to our external table. And so this is an overall view of the application as far as how the observers are chained together. So some sort of RIA client ingests triples into the system. There's a triple observer which is in charge of matching those triples with the corresponding statement pattern that matches it, or just discarding it if there's no statement pattern that matches it. That statement pattern then those triples are written to the statement pattern column, and then there's a statement pattern column joins those results together and writes those results to either a filter column or a join column, and then the filter observer and join observer spring into action. And the path that your updates take through this chain of observers in large part has to do with the metadata that's written to the table for the particular query. At the end of the day, either the join observer or the filter observer are going to be at the top of your query, and they end up pushing the results to the query result observer, which is in charge of pushing the results to the external Accumulo table. So here's just an overview of the RIA architecture with the Fluo app included. You have a precomputed join client which registers the Fluo query, inserts the metadata, scans the core RIA tables to get the intermediate results up to state with results that have already been inserted into the system. Statements are streaming in. They first get inserted in the core tables, then inserted into the Fluo table. And finally, you have a RIA client, which is issuing queries to the system and using precomputed joins where it can to get boost in performance. So this is just a sequence diagram that kind of further illustrates the layout. You register your query, you then scan the core RIA tables for historic results, and then you insert those statement pattern matches into the Fluo application. Those results then percolate up. As they come out of the top, they get exported to the precomputed join index. So this sequence diagram just adds an extra layer of complexity where now we're allowing streaming to occur while we register our query. And the takeaway from this slide is effectively that the system will be consistent so long as you register the query as a single atom of work and first write your result to the core RIA table before writing to the Fluo application. And this slide just indicates some of the boosts in performance that you can get by using precomputed joins. So here we had 5 proprietary queries that we issued to proprietary data. The first query is the most complex. It consisted of 14 joins, 6 of which were left joins. And the left column here is the average query time over 10 iterations using RIA with 1 precomputed join, which exactly matched the query. And the column on the right is RIA with no precomputed joins. And as you can see, you can take rather complex queries and reduce them down to second to sub-second time by using precomputed joins. So now that I've talked a little bit about precomputed joins, materialized views, and RIA, I want to talk a bit about the Entity-Centric Index. So the ideas for our Entity-Centric Index were taken from Facebook's Unicorn paper, and to motivate those ideas, I want to talk a little bit about the problem of finding documents with some specified collection of terms. So the idea is you have some graph which consists of documents and terms where edges are directed from documents to the terms that they contained. And you can represent this as a collection of adjacency lists. And the idea here, if our terms are dog and bark, and you want to find documents which contain dog and bark, you just find the intersection of these lists, right? Well, what happens if these lists grow really large, right? Well, we want to come up with some way of distributing the problem. So then what we can do is we can basically come up with some sort of sharding strategy where, in this case, we're just sharding on the document number. So all things with remainder 0 when modded by 3 get sent to server 1, remainder 1 modded by 3 gets sent to server 2, and so on. And the idea is then you now have much shorter lists that you're dealing with on each server, and you're finding intersections of much shorter lists. So essentially, one of the key ideas that the Unicorn paper spelled out is just the idea of a distributed document partition index. And Accumulo has a nice framework in place for implementing document partition index. This is described in the O'Reilly book that they're signing out in the hallway here in, I guess, another hour or so. And it uses the key design that I've indicated at the bottom. But the sort of the special sauce that makes that design work is the index document iterator, or more generally, the intersecting iterator. And I'll describe that in detail a little bit more here in a second. So the idea behind an intersecting iterator is it's effectively just a collection of iterators, right? And so if we're trying to find all documents which contain the terms dog and bark, essentially we have an intersecting iterator on each server, which is a collection of iterators. Here we have one iterator which scans for the column family bark and another iterator which scans for the column family dog. And we have an intersection when the row IDs and the column qualifiers are equal. So on server 1, we have iterator 1, it stops in the column qualifier 6 for bark. And we have iterator 2, it stops initially when the column qualifier is 3, right? And we see that we don't have an intersection there because the column qualifiers are different. So then because the column qualifier for iterator 2 is less than the column qualifier for iterator 1, we increment the iterator 2. When we increment iterator 2, we then see that the column qualifiers are the same and the row IDs are the same. So we have an intersection, and we pass back document 6. Similarly, on server 2, iterator 1 stops at bark with column qualifier 1, then iterator 2 stops at dog with column qualifier 4. We see that we don't have an intersection. Even though the row IDs are equal, the column qualifiers are different. We see that the column qualifier of iterator 1 is less than the column qualifier of iterator 2. We increment iterator 1, and now the column qualifier is 4. Column qualifiers and the rows are equal, we have intersection, we pass back our result. And that's the general idea. So you're effectively performing a merge join on the server. So our idea was just to take this and extend it to RDF data. So here we're asking, we have a Sparkle query which asks for all people who have a dog as a pet, who drive an SUV, who are employed by the US government. And we have some RDF data that's related to that query. And we sort of take a similar approach. We say, okay, well, let's represent this RDF data as a collection of adjacency lists. We're including the predicate. So what these adjacency lists represent is that the predicate is has pet, and object just indicates that dog is the object of the triple. And we have employees subject US government. employs as the predicate, subject implies that U.S. government is the subject of the triple, and so on. And the idea here is we just want to find the intersection of these lists to get our query results, and we see that our intersection is going to be person 2 and person 4. So how do we apply that to Accumulo? So for our entity-centric index, for every triple we insert, we actually enter it twice into our entity-centric index. So there's definitely some data duplication going on there, but I'll explain why we do that in a second. So we essentially write the data so that the subject occurs in the row, the predicate occurs in the column family, and the object occurs in the column qualifier. And then we reverse the position of the object and the subject. So to see clearly what's going on, look at the example at the bottom where we have a triple that we insert. We have John works at Parsons with a graph context Parsons employees, and we get the following 2 entries in our Accumulo table. So here, so here the word object and subject, which appear in the column qualifier, just indicate what part of the triple is actually written in the column qualifier. So just to kind of complete the parallel example with what we did with documents in terms, now we have an intersecting iterator within our entity-centric index, and our first iterator scanning for the column employees with column qualifier subject U.S. government. The second iterator is scanning for drives with column qualifier object SUV, and the third iterator is scanning has pet with column qualifier object dog. And we have an intersection when the row IDs are all equal. So we can see on server 1 we pass back person 2, and on server 2 we pass back person 4. So the reason that we duplicate our data in the way that we do is so we can solve the following 3 query types. So we call these properties for an entity. So all statement patterns have a common constant occurring in the same position. Occurring in the same position. Entities with properties, so all statement patterns have a common variable occurring in the same position. And then friends of a friend queries where all statement patterns have a common variable, which can occur in the subject or object position. We don't allow the predicate to be a variable in any of these cases. And so we use our entity-centric index much like we use our precomputed join index. We essentially take our query, and during query planning we say, okay, well, let's bin up the statement patterns which have common variables or common constants which meet our entity-centric, which are one of the entity-centric query types that we describe here. And we basically combine those into an entity-centric index node, and we delegate those to the entity-centric index. So in this case, we're binning up, we have 2 bins of 2, and we bin those up into entity-centric index nodes, and we're taking our query and we're reducing it to one with only one client-side join, but there are still joins that are going to be going on the server. So this slide here just indicates some of the boost in performance you can get from using our entity-centric index. So here we ran 13 queries against the Lehigh University benchmark data set, which consists of about 33 million triples. These 13 queries, these were queries that we made up. These aren't to be confused with the Lubbock benchmark queries. They're star queries which have the entity-centric form that I've described. And as you can see, with the exception of a few cases, you pretty much get a significant boost in performance across the board, except for in the middle there. So next steps, as far as future research is concerned, we want to look at ways to determine precomputed joins in a somewhat automated fashion, maybe by calculating, coming up with ways to efficiently calculate frequent subgraphs, which efficiently doing that is maybe not possible, but maybe developing some sort of query logging framework and coming up with ways to do some sort of syntactic analysis in the queries that get logged. And then streamlining our query planning with respect to precomputed joins. So I mentioned that for precomputed joins, the matching is implicit in that you're matching the representative query of the cache result with subqueries of the query that's issued by the user. So come up with ways to do that efficiently and minimize the search space for determining query plans which use precomputed joins. Next steps for the entity-centric index include exploring ways to improve join performance across entity-centric index nodes. We found that for query plans which form multiple entity-centric index nodes, the join performance across them tends to suffer. Maybe adding a capability to make the entity-centric index allow users to define explicit notions of an entity. So we're not putting any restrictions on the collections of properties that entities have, or forcing users to register notions of an entity from maybe an OWL like class perspective, and maybe adding an extra layer capability to do that, and leveraging that to maybe boost query performance and just provide a more rigid schema. Future research in general, as far as server-side join evaluation is concerned, is maybe leveraging Spark to come up with some sort of query evaluation framework for performing joins server-side by maybe joining RDDs together in some way. So thank you all for coming. That's basically it for my talk. So questions, concerns? No, so that's a good question. So that is data dependent, right? The sharding is effectively, currently, the way that sharding is handled is it's done.
Can you repeat the question?
Oh, I'm sorry. The question was about sharding for an entity-centric index, and the answer is that it's data dependent in the sense that really the row, whatever is in the row, is sort of handling the sharding, and sort of first pass. So on average, the hope is that the data will sort of more or less distribute your triples in a reasonable way. But there are definitely cases where things could get bad, and so that's certainly something we need to look into. Any other questions? Okay. Well, again, thank you guys for coming.